This video explains SHAP and our new visual designs used in Step 6 of our Learning-From-Disagreement framework. Considering the following fixed scenario for a spam filtering application, we have 5 data instances, which are 5 emails. From each of them, 3 features have been derived through feature engineering to train the spam classifier. For example, the first email contains 46 words, 2 URLs, and 2 numerical values. The spam classifier takes an instance as input and outputs the logouts as the prediction. Through a sigmoid function, we get the final probability value. SHAP interprets the prediction by fairly redistributing the logouts value back to each feature of the data instances, as you can see on the right table. Here, if we sum up the SHAP values from the 3 features, we get the logouts of the instance. Similar interpretation can also be applied to other instances. To the end, we get a SHAP matrix, which has the same shape with the input data. Note that the SHAP value could be both positive and negative. Positive values indicate the corresponding feature value increased the probability, or say contributed positively. Negative values contributed negatively, and those cells are filled with line patterns. Let's now focus on single feature, an URL, and visualize its impact through the traditional summary plot. First, we map the feature values to colors from blue to red. Second, we use a point to represent each instance and place it along the horizontal direction according to its SHAP value. After putting more instances into this visualization, we can easily draw conclusions about the feature from the instance's collective behaviors. For example, in the current case, we see the emails containing more URLs are more likely to be spam, because red points with larger NURL values have larger positive contributions to the spam probability. The visualization can also be used to interpret the discriminators from our framework, because our discriminator is also a classifier. In this case, the positive and the negative labels are A minus B plus and A plus B minus respectively. The features here are meta features, as the model training features may not be available during comparison. For example, assume we do not know what features were used to train the 2 compared classifiers, A and B, but we believe the number of capitalized words affect the classifier's behavior. We can then derive this feature and use it as a meta feature to probe the difference between model A and B. From the current visualization, we know that compared to A, model B tends to capture spam from emails with more capitalized words. This comparative interpretation helps to select models and better ensemble them. The summary plot is an effective visualization, but it may not scale well. If we have many more points, they will be all plotted and stacked in the limited space. The resulting visualization become misleading. For example, this is a real visualization result. From 8, we can see large values in red always contributed positively. However, the fact is that there are many red points being plotted under the blue ones on the left. We propose a new visual design to address this issue. Specifically, we build a 2D histogram for all points based on their feature value and SHAP value. Each bin of the 2D histogram is represented as a bubble, whose size denotes the bin size. The color of the bubble reflects the feature value. This way, we significantly reduce the number of elements need to be drawn. These bubbles are then packed horizontally based on their SHAP values. Existing circle packing algorithms can sequentially place those bubbles in tangent to each other without overlap, as demonstrated by this animation. We can also use the force-directed algorithm to dynamically adjust bubbles' positions and resolve their conflict. The final visualization solves the overplotting issue, and one can flexibly adjust the bin numbers to control the visual appearance of the visualization. One limitation of the visualization is that the cumulated area of bubbles cannot accurately reflect the data distribution due to the size mapping of bubbles. We propose an area plot visualization, which presents the data distribution across different SHAP values. Each SHAP bin is represented as a rectangle. The head of the rectangle denotes the bin size, and the color of the rectangle is blended from all bubbles in the corresponding bin through a weighted sum. Horizontally stacking all rectangles, we get an area plot. Increasing the granularity of the SHAP bins, we get the final area plot. The area plot and the bubble plot together build up our overview plus detail visualization. The meta feature from the TP and FP discriminators are presented as two columns of error plots. The same meta feature from the TP and FP sides are connected through Bezier curves. Clicking any error plot will show its details in the bubble plot. Both circle packing and force-directed layouts are implemented in this view. And one can flexibly change the number of feature bins or SHAP bins to explore the feature at different granularities. Interacting with the transfer function legend will change the color mapping or select bubbles within certain value ranges. From this view, we can easily draw conclusions on the two compared models. For example, the current feature is CTR set ID, and the two compared models are tree and RNN-based CTR models. The feature realization shows that RNN behaves better than tree on the website with higher click rate. Knowing this detail is important for model comparison, selection, and assembling. Please check more details of our design and exploration cases in the paper. Thanks for watching.